This is Katie with Smart Addition Academy, and today we are going to be covering acids and bases. All right, in this session, we are going to be talking about acids and bases, and we're going to break this up into 4 parts. The first part is acid and base characteristics. The second part is pH scale. The third part is acid and base equations. And the fourth part is classification. And with respect to your time, we are going to jump right in so I can try to get this done for you and cover all the basic information just as quickly and efficiently as possible. So, what are acids? Acids donate hydrogen ions in an aqueous, which is water, solution. So when you put an acid in water, it's going to donate hydrogen ions. It's going to break off a hydrogen ion from the acid. And by doing so, it increases the hydrogen concentration in the water. So you can see the little droplet here. Imagine dropping that in, and all these hydrogens break off, meaning that there's a lot more hydrogens in the water now. Some common acids are acetic acid, CH3COOH, acetic acid, nail polish remover and vinegar, hydrochloric acid, HC3, HCl, stomach acid, phosphoric acid, which is H3PO4. It's in detergents and soft drinks, and nitric acid, HNO3, which is in fertilizers. So one thing I want to point out really quickly is you might notice a pattern of repetition here in those chemical formulas. If you take a look at hydrochloric acid, phosphoric acid, and nitric acid, all of the acids start with an H. Now remember, when we put those acids into water, that H is going to break off and the hydrogen concentration in the water will increase. Now, acetic acid is a little different. However, if you take a closer look at that, CH3COOH, that H on the end there, that's the one that's going to break off. So it doesn't start with an H like the others, but it does have that loose H there that will break off in a water solution. All right, now we talked about acids. What are bases? Bases form hydroxide ions in an aqueous solution. So just like acids, where they are going to release that hydrogen when put into water, bases are going to release OH, which is also called hydroxide, when they're put into water. So the OH is going to break off, and then when you put a base into a water solution, you're going to increase the OH concentration. Let's take a look at some common bases. Sodium hydroxide, NaOH, which is in soap and oven cleaners. Potassium hydroxide, KOH, which is in soap and textiles. Ammonia, NH3, which is in cleaning agents and fertilizers. Or magnesium hydroxide, which is MgOH2, laxatives and antacids. So these are some common ones. And again, you might notice a pattern of familiarity with the chemical composition of these. As you take a look at the chemical formulas, you'll notice a pattern. The NaOH, KOH, and MgOH, you'll notice that OH as a part of the chemical formula. Remember that those are bases because as you drop them into the water, that OH is going to separate, increasing the OH concentration in the water. Now, ammonia is a little bit funny one. It's kind of one that doesn't quite fit the standard there. It still does release the OH, and we'll talk about how later on in this session, but it is one that classifies. Now, you might not have to memorize all of the chemical formulas of all the acids and bases, but I highly do recommend that you memorize some very common ones. Ammonia would be a very common one, and sodium hydroxide that you're going to see quite often. As far as with acids, hydrochloric acid is something you'll see quite often as well. And we'll go over a few more as we go through this session. So we talked about what are acids, what are bases. Now we're going to talk about a few characteristics that make them different as well. So obviously the most different about them is that acids are going to release hydrogen when placed in water, and bases are going to release hydroxide, which is that OH when released in water. Here's some other things that make them different. Acids have a sour taste. So common acids like stomach acid or citrus are acidic, and they have a sour taste. They will sting or burn on contact. They have a pH that is less than 7. And when we do the litmus paper test, they will turn the blue litmus paper into red. And we'll talk a little bit more about the litmus test in just a second here. With bases, they have a bitter taste. So a common base is soap. Soap has a bitter taste. It feels slippery. It has a pH greater than 7. And when we do the litmus paper test, it turns the red litmus paper into blue. Bases also release hydroxide ions in the water. Quick interruption to remind you that the science portion of your upcoming TEAS exam will test you on not just acids and bases, but also A and P, biology, scientific reasoning, and other chemistry concepts like balancing chemical equations, the trends of the periodic table, and more. Get everything you need to prepare for and pass your upcoming TEAS exam by using our online TEAS course available at www.smarteditionacademy.com. So let's talk about that litmus paper test. So litmus paper is these little strips of paper that you can dip into a solution to find out if it's acidic or alkaline or base. Alkaline and base are interchangeable words that mean the same thing. So with the litmus paper, it's actually stained with a substance called litmus, and that causes it to change colors in different solutions. So you have a red litmus and a blue litmus piece of paper, and when you dip those into acid, the red will stay the same. However, the blue paper will turn red in an acidic solution. In water, because it's neutral and neither acidic or alkaline, it's going to stay the same. And in an alkaline or base solution, the red is going to turn blue and the blue will stay the same. So this is just a little test that you can use to demonstrate this. You can look this up on YouTube as well. It is fun to see the color change in the paper, to see it change from one color to another in different solutions. All right, and look at that. We're already done with section 1. Good job for making it through that. We are going to go on to some practice questions. So how this will work is I will put the question in 10 seconds up on the screen just for you to read it through by yourself. And then I will talk about the question, maybe some important parts that we need to pull out of the question or key terminology, vocabulary. And we'll talk about the answer choices and reveal which one is the correct answer choice. And we will go ahead and get started with question number 1. All right, the question says, which of the following is an acid? So you might not have all the chemical formulas memorized. I do recommend memorizing some very common ones. However, there are some tips and tricks to help you kind of use process of elimination if you do not have the chemical formulas memorized. So remember with bases, they're going to contain an OH in a lot of their formulas. And with acids, they're going to start with an H at the beginning. So let's take a look at our answer choices here. We have KNO3, BaCl2, NaOH, or H3PO4. Okay, which one of these would fit that classification of starting with an H, meaning it is likely an acid? And that would be answer choice D, correct. So if you said answer D, that is phosphoric acid, H3PO4. Here's our next question. Which is a characteristic of a basic solution? Does it taste sour, accepts OH ions, turns litmus blue, or contains a lot of H3O plus ions. So let's talk about some different characteristics of acids and bases again. Acids are going to taste sour. So this is the question's asking us about basic solutions. So we can go ahead and process of elimination, take off answer A. Now, accepts OH ions. Now, bases do have to do with OH ions, but not accepting them, they release them. So bases like NaOH are going to release that OH into the water and create a higher concentration of OH, which is also called hydroxide in the water. So we can go ahead and take off B. The last one I want to go ahead and do process of elimination to take off is D. H3O is the product of what happens when an acid is put into water. So an acid releases that H plus proton and it releases it into water, which is H2O. You've probably heard of that before. So H2O, and you add an H into it, a lot of the times what happens is that extra H bonds onto the H2O, creating H3O. So a lot of the times acids and water will create H3O. Again, that doesn't have to do with this question because this question is asking us about a basic solution. So the correct answer is C, that it turns litmus paper blue. It turns red litmus paper blue is the sign that you have a basic solution. Let's go on to our next practice question. A researcher identifies an unknown solution to have a pH of 3. What characteristic does the researcher most likely write down about the solution? Does it taste sour? It's a weak electrolyte, minimally corrosive, or slippery to the touch? So through process of elimination, let's go ahead and take out weak electrolyte and minimally corrosive. These are terminologies that we haven't quite covered, and that's because they actually belong to both acids and bases. So those apply to both, and we are talking about an acidic solution. We know that because the pH of our unknown solution is 3, and acids have a pH of less than 7. So this pH of 3, this solution is going to fall in the category of an acid. Now we need to determine if it is going to have a sour in taste or a slippery to the touch. The characteristic that most fits acids would be sour in taste. And now let's hope that this researcher didn't taste his unknown solution. That would not be very safe. But he did test the pH and found a pH of 3, meaning he could assume that it is sour in taste. All right, here's our next question. Which of the following is a characteristic of a citrus substance? Citrus is acidic. So which of these would be a characteristic that you would find in an acidic substance? Would it have a pH of 7? No, that's for a neutral substance. Would it turn litmus blue? No, that's what base solutions do. They turn red litmus into blue. And slippery to the touch is also a characteristic of a base solution. So that leaves us with taste sour. Here's our next question. All right, which of these would turn litmus paper blue? All right, so it's basically asking you to identify which one is a base, because bases turn red litmus paper into blue. So if you don't have all of these chemical formulas memorized, that's okay. We can use our handy trick, which is that a lot of the times acids are going to start with an H and bases are going to contain an OH. So let's take a look at our answer choices. We have HF, hydrofluoric acid, KOH, potassium hydroxide, HNO3, or C3H6O3. So taking a look at these, we are looking for a base because it's turning the litmus paper blue. So we're going to go ahead and eliminate the ones that we know are acids based on our little trick of starting with an H. So we can take off A and C. Which of those remaining chemical formulas have an OH indicating that they are a base? If you said B, that is correct. KOH, potassium hydroxide, is a base solution, and it would turn litmus paper blue. All right, we have officially finished part 1 of this session. You all are doing fantastic. Thank you for your participation. I greatly appreciate it. And we are going to be as respectful to your time as possible and jump right into section 2. We'll cover some information and do some more practice questions together. The next section we're going to talk about is the pH scale. So the pH scale is a quantitative measure of how acidic or basic a solution is. The pH scale runs from 0 to 14. Anything from 0 to 6.9 is going to be acidic, and anything 7.1 to 14 is going to be alkaline. Remember, alkaline is just another word for base, so you can interchange those words as acidic or basic or alkaline. Now, 7 in the middle is neutral, and there's a few neutral substances, but the very most common is pure water. It has a pH of 7, making it neutral in the center. So everything below that point is acidic, and above that point is alkaline or basic. So every solution has a pH. Below are some common household items and their pH. Water has a pH of 7 and is considered neither an acid or a base, but it is instead a neutral substance. So water's in the middle, it has a 7. We have common things like stomach acid with a low pH of 1.2, lemon juice 2.2, and vinegar 2.8. These are all acids. And on the other side of the spectrum, you have things like baking soda with a pH of 9, soap with a pH of 10, or bleach with a pH of 12.5. So everything has a pH. Water is that very special one that rides right in the center, and it is really neither an acid or a base. It's more of a neutral solution. But because it can kind of teeter between the categories of acid and base, it is also categorized as amphoteric, which means that it can sometimes act as a weak acid or a weak base in a reaction. So it is, you'll need to know this vocabulary word, amphoteric. And what that means is that because it teeters right in between the line of acid and base, it teeters between those, it can sometimes act as either in a solution. And we'll talk about that when we talk about equations in just a little bit more. But that vocabulary word will be important to remember. All right, let's continue. What does pH stand for? So you've probably heard of pH before. pH is a common terminology. We even see it on things like shampoos and body wash, soaps, all kinds of different things, talking about pH balance. And so what does pH actually stand for? So pH stands for the power of hydrogen. So pH is the measure of the hydrogen atoms in the solution. Solutions with a very high number of hydrogen atoms will be more acidic. So acids can be classified as weak or strong based on their pH value or their hydrogen concentration. Bases can also be classified as weak or strong. So what this means is if an acid is weak, it's going to have a low concentration of hydrogen. However, if you have a strong acid, it's going to have a high concentration of hydrogen. So the power of hydrogen has to do with the concentration of hydrogen in the solution. There's all different kinds of acids. We have acids starting with a pH of 1, like hydrochloric acid. You have sulfuric acid with a 2.5, hydrofluoric acid with a 3.4, and acetic acid with a 4.8. So all of these are acids, but their pH is going to range from anywhere from 1 to nearly 5. So some of them are going to be very strong acids near that lower pH mark, and some of them are going to be weak acids near that higher pH mark. Strong acids are going to completely ionize in water. What that means is they will completely come apart, while weak acids will only partially ionize. So let's take a look at two examples here. We have hydrochloric acid. If we dropped hydrochloric acid into water, what's going to happen is all of the hydrogen and the chloride ions are going to separate. You're going to have an acid to start with where they're together, and then you're going to have the hydrogen, which is a positive proton, and the negative chloride ions. Now, that is what a strong acid will completely come apart. However, a weak acid will not come apart quite as much. So let's take a look at the other example, which is hydrofluoric acid, HF. In a weak acid, if you dropped hydrofluoric acid into water, you're going to have some of them that stay together while some of them ionize or come apart. And we will now talk about bases, which is very similar to acids in the way that they behave as well. Different bases have different pHs. You have pHs like zinc hydroxide, which has an 8.8 pH, ammonia right in the middle with an 11.5, and sodium hydroxide with a pH of 14. So all of these are going to be from a weak base, closer to that 7 mark. So in this example, zinc hydroxide is our weak base. And then you have very strong bases, which are going to be at the end of the pH scale, closer to that 14 mark. All of these are bases, but they can range from 8 to 14. And bases act a lot like acids in water. Just like the strong acids, strong bases completely break apart in a process called dissociation. Now, remember how we said that strong acids ionize, break apart, and strong bases dissociate, which also means break apart. Two different vocabulary terms there, but they both mean the same thing. Strong acids and strong bases will both fully come apart when placed in water. However, weak acids and weak bases will only partially dissociate or ionize, which means to come apart. Let's take a look at our examples here. We have sodium hydroxide, and when sodium hydroxide is placed in water, it is a strong base. And so you're going to break apart the sodium and the hydroxide. You'll end up with positive sodium ions and negatively charged hydroxide ions. Remember, bases increase the OH concentration. And you have weak bases like zinc hydroxide, which will only partially dissociate, meaning that you'll have some that are still together and you'll have some that are separated into the zinc ion and the hydroxide ion. All right, we are ready for practice questions for our part 2. Again, I'll give you a few seconds just to read over it yourself, and then we'll talk about the question and our answer choices through each one. Get ready, get set, and go. Which partially dissociates into hydroxide ions in an aqueous solution? So, which partially dissociates? Okay, so what it's asking us is which one is weak? Partially, not fully. Now remember, strong acids, strong bases are going to fully come apart. Weak acids and weak bases are going to partially come apart. Now, it does use the terminology dissociate, which we're going to link with a base. Also, another clue that is at a base is that it dissociates into hydroxide ions. Remember, it's going to have one part that is an ion and one part hydroxide ion. So we're going to try to figure out which one of these is a weak base. We have KOH, HClO4, C5H5N, or H2CO3. It is very helpful to memorize some of the common acid and base chemical formulas, but if you don't have them memorized or you don't remember some of them, that's okay. We're going to use our nifty little trick, which is that most of the time, acids are going to start with an H. Let's take a look at our answer choices again, and that tells us that through process of elimination, we can go ahead and take out B and D. What we're left with is KOH and C5H5N. Okay, if you don't know what C5H5N is, it's pyridine, and KOH is potassium hydroxide. Between these two, which one is going to fully disassociate and which one will partially disassociate? KOH is going to fully disassociate. It is a strong base and it will fully come apart. It is one helpful that you'll need to memorize that one. That is one that is used quite often, quite commonly. Now, C5H5N is pyridine, and it will only partially disassociate. So in the answer box, if you said C, you are correct. That one can be a bit tricky though. So if you did say A, I do understand why. Just remember, we're looking for a weak base, not a strong base. Okay. All right. Here is our next question. Which solution has a pH of 7? We have a few different solutions here, but what we remember about our pH scale is that it goes from 0 to 14, and right smack dab in the middle is 7, which is pure water, neutral solution. So good job. Those that said C, that is correct. All right, our next question asks, the strength of a base is determined by its ability to turn litmus paper blue, feel slippery to the touch, completely ionize in water, or disassociate into hydroxide ions. So when we're looking at our answer choices here, this one can be a little bit tricky. All right, so which one is, let's read our question again. It says the strength of a base. Not if it is a base, but the strength of the base. So for answer choice A, bases do turn litmus paper blue, but they are not going to tell you the strength of the base. Also, answer choice B, bases do feel slippery to the touch. However, all bases, from a weak base to a strong base, are going to feel slippery to the touch. So that's not going to tell us the strength of a base. Our last two answer choices are completely ionize in water or disassociate into hydroxide ions. Ionize in water has to do with acidic solutions. And so that leaves us with answer choice D, which is disassociate into hydroxide ions. Now remember that the strong bases are going to completely disassociate, meaning that there's going to be a lot of OH in the aqueous solution. However, weak bases are only going to partially disassociate. That means you're still going to have some of the acid molecules, and then you'll still have some that are the broken apart OH and other ion. So with a strong base or a strength of a base, you're going to determine how much hydroxide ions are in the water. All right, let's go to our next question. Using the following image, what substance is most likely a weak acid? So we know that 7 in the middle is neutral. Below 7 is acidic. And as we get closer to that 0 mark, the acidic solution is going to become more acidic. So that lower pH is more acidic, and closer to 7 we get on that scale is less acidic. So it's asking us which one is a weak acid. And we look at our antacid, borax, milk, and salmon is a pH of 6, which means it's close to being neutral, but still on the acidic side, meaning it is a weak acid. So good job if you said D. Next question. Which of the following would completely ionize in a solution? All right, from our question completely. So we're looking for strong. Ionize. So we're looking for acid. Strong acids completely ionize. So which of these would be a strong acid? Okay, we have HF, HCl, N2H4, or C2H4O2. So if you don't have them memorized, that's okay. We're going to use our nifty trick that we're going to know that our acids are usually starting with an H. So we can kind of take a look here, and we know that HF and HCl are acids. HF is hydrofluoric acid, and HCl is hydrochloric acid. Which of these is going to be a strong acid? And that is going to be hydrochloric acid. Hydrochloric acid is one that would be very good to memorize. It's used quite often as in examples and in questions because it is very common. And is a perfect example of a strong acid that would completely ionize in water. So if you had answer B down, that is correct. All right, here's our next question. Water can act as an acid or a base, and because of this behavior, it is known to be, and your answer choices, amphoteric, aqueous, ionic, or pure. So water is aqueous, but it's always aqueous. So that doesn't have to do with this question in particular. Ionic and pure have to do with different charges, and pure water is, in this case, that's what we're talking about, but it is which one has to do with the question, which is acid or base. It can act as an acid or base. And that's our vocabulary word that we learned earlier, which is amphoteric, meaning that a water, because it teeters between acid and base on the pH scale, that in some solutions it can even act as a very weak acid or a weak base. All right, here's our next question. How do researchers determine the strength of a base? Determine the pH value, observe the litmus color change, observe whether ionization occurs, or measure the hydronium ions in the solution. So let's talk about our answer choices. Determine the pH value. The pH value would determine whether you have a strong base or a weak base. And you would know that because a pH that was closer to that 7 mark is going to be a weak base, while a pH that gets closer to that 14 is going to be a strong base. Let's check our other answers just to make sure. Observe a litmus color change. While litmus color changes can tell us if a solution is basic or acidic, it doesn't tell us how strong it is. It just tells us whether it falls in the category of acid or base. Observe whether ionization occurs. Ionization is the process that acids go through as they lose their hydrogen in a water solution. So that is not to do with a base or the strength of a base. And measure the hydronium ions in a solution. Hydronium ions also have to do with acids. As they release that H, a lot of the times that extra H proton will combine with H2O to make H3O, which is hydronium. So if you said determine the pH value, you are correct. pH value would tell us whether we have a strong base or a weak base. Here's our next question. Which of the following is a weak base? Vinegar, ammonia, pure water, or sodium hydroxide? All right, so taking a look at our answer choices here, we're going to use process of elimination to take off 2 of our answer choices, and that is vinegar and pure water. Vinegar is acidic, so it is not going to be classified as a base. And pure water, remember, is not technically an acid or a base, but more of a neutral. So we're left with ammonia or sodium hydroxide. This is going to be one of those situations where memorizing some of the chemical formulas are definitely going to play an important role. Ammonia is NH3 and sodium hydroxide NaOH, which both of these are used a lot in equations as they're common substances. And through those processes, we're going to know that the strong base is sodium hydroxide, NaOH, making the weak base ammonia. Here's our next question. Which of the following measured pH values means the solution is basic? So if you had these 4 different solutions and you tested the pH of each, you had one with a pH of 2, a 5, a 7, and a 9. Which of these would be the basic solution? We know that the pH scale ranges from 0 to 14. 7 in the center is neutral. Anything below 7 is acidic. And anything above 7 is basic or alkaline. So those that said D, good job. Yes, 9. If you had a pH of 9, you would have an alkaline or base solution. Here's our next question. What is the pH of a neutral solution? So that pH scale runs from 0 to 14. 7 is our middle marker, which is a neutral solution. So those that said C, good job. C is the correct answer for 7. Our next question. Which of the following is a strong acid? We have HF, HCl, H3PO4, or CH3COOH. So we have all acids here. So this one can be a little bit more tricky in the question. Again, this is going to come into play where it's going to be handy to memorize those chemical formulas of some common strong and weak acids. That way you'll know which ones are strong and which ones are weak. So we have HF, HCl, H3PO4, which is phosphoric acid, and CH3COOH. Of these 4 acids, the one that is considered the strong acid is HCl, which is hydrochloric acid. You're going to see that in a lot of different examples and questions. It is a very common one, so I definitely would memorize that that is a strong acid and memorize the chemical formula for that acid. All right, let's move on to our next question. Bleach has a pH of 13, and this indicates that bleach is a weak acid or weak base, a strong acid or a strong base. Remember that pH scale goes from 0 to 14. Anything below a 7 is acidic. So this is already telling us that it must be alkaline or base because it has a pH above 7. Now we need to determine if it is a weak base or a strong base. So alkaline runs from 7 to 14. Anything above a 7 is going to be basic or alkaline. If you're closer to that 7 mark, you're going to be a more neutral solution. Whereas if you're closer to that 14, that higher mark, you're going to be a strong base. So pH of 13 is very close to that far end, meaning that the bleach is going to be a strong base. So those that said D in your answer choices, good job. We are on our very last question. Which of the following indicates a solution is acidic? The litmus paper that turns purple, litmus paper that turns blue, a measured pH value equal to 7, or a pH value less than 7. So litmus paper that turns purple is not applicable here. Litmus paper that turns blue is going to be a base. Bases turn red, litmus paper blue. A pH equal to 7 is going to be a neutral pure substance like pure water. And that leaves us with answer choice D, which is the correct answer choice, that the measured pH value less than 7 would mean the solution is acidic. All right, good job, guys. You all are doing fabulous. Thank you for hanging in there and for your participation. I certainly appreciate it. I'm trying to be as efficient and respectful to your time as possible, so I'm going to just keep on rolling through our section 3. We have 2 more to go. We have section 3 and section 4, and we will get wrapped up pretty soon. So our section 3 we're going to cover is acid and base equations. Now I'm going to go ahead and preface this, that this can be one of the most tricky categories when it comes to acids and bases. There's a lot of formulas, and if you don't have the formulas memorized, can be more tricky. So I definitely recommend making yourself a little chart, maybe some flashcards or some things to go over to also help you memorize those chemical formulas of some very common acids and bases. All right, so let's talk about first how acids react in water. And we've talked about that a little bit, but let's go over it again. When acids are put into water, the acid loses an H+. The hydrogen often combines in the water with H2O, creating H3O, which is hydronium. Here's some great examples that you can visualize how that happens. So acetic acid in water, CH3COOH plus H2O. That CH3COOH is going to drop that last H, and that hydrogen is going to combine with H2O to form H3O. As you look down here, I'll let you look through those: hydrochloric acid and water, phosphoric acid and water, nitric acid and water. You'll see the same pattern. That H is dropped off from the acid and is combined with H2O to form hydronium, which is H3O. Bases in water are going to lose their OH, which is hydroxide. Or there are a few circumstances where they can accept an H. So, for example, the acid will donate the H, gives it away. The base can accept the H, or the base can drop off their OH. So let's take a look at some formulas here. Sodium hydroxide, NaOH, plus H2O. What's going to happen is that Na and OH are going to come apart. Now, I did not put water as one of the products in this because it is still there. But what I wanted to show you most was that NaOH break apart. Potassium hydroxide in water. The K and OH will break apart. And then ammonia in water. Ammonia is one of those kind of funny ones that doesn't quite fit the normal classification. So it doesn't have that OH in its formula like the other bases do. And it doesn't drop an OH, but what it does do is it accepts an H+. So look at that, NH3 plus H2O. What you're going to end up with is that the H2O gives it one of its hydrogens, meaning now you have NH4 and OH left. Just like any other base solution, you're still going to end up with OH as one of your products. It just functions just a bit differently. Magnesium hydroxide, MgOH, is going to break up into Mg and OH. So with acids, you're going to end up with a hydrogen that is broken apart, and that hydrogen often combines with H2O to make H3O. And with bases, you're going to have the base break apart to have an ion plus an OH hydroxide. All right, now that is what we just covered before, was acids or bases in water. So when you put an acid or a base in water, that's what happens. What happens when you combine an acid and a base together? That's a process called neutralization. And that's when you end up with H2O and a salt. A salt is an ion that is left as the product of an acid and base reaction. So acid plus a base, your products are going to be a salt, and H2O. So remember before we were talking about if you put an acid in water, you're going to have the ion plus the dropped H proton. If you put a base in water, you're going to have the ion plus the OH as they came apart. When you have an acid and base combined together, you'll have a salt and H2O as your products. So let's take a look at it as an example here. HCl, which is hydrochloric acid, and NaOH, which is sodium hydroxide. If you combine these two together, you're going to end up with NaCl and H2O. You can find out how those two products are made as you take a closer look at the molecules on the screen. Starting with the first one, we have the red molecule and the blue molecule, HCl, and NaOH as the purple, green, and blue as well. What happens with a neutralization is that the H is dropped from the Cl, and it combines with the OH from the Na, making H2O, water. And what's left, the two products then connect together, the Cl and NH connect together to form the salt. All right, I know that was a lot to take in. Let's go over some practice questions, and we'll talk about the questions and work through them again, and then we'll go over the question and the answers afterwards. Okay, I'll give you a few seconds to read it to yourself first, though. So what product is formed when acetic acid reacts with water? So when an acid reacts with water, an acid is added to water, the H drops off. Okay? And that H, a lot of the times, will combine with H2O and make H3O. So what is resulted is the acid minus the H. Okay, so let's take a look at our answer choices here. We have H2, OH, CH3COO, or CH3COOH2. Okay, so which product is formed when it reacts with water? Well, we know it's not OH because OH is when bases react with water. They release OH. We can go ahead and take that off. We know it's not D because somehow that would have gained a hydrogen. See how that H now has a 2 on the end? That means it has gained a hydrogen. We didn't gain a hydrogen. So we're left with H2 or CH3COO. And when we talked about the hydrogen is dropped from the acid, from acetic acid, the hydrogen often combines with H2O to make H3O. So our correct answer choice is going to be CH3COOH. It's basically the acid that just lost the H. All right, here's our next one. What is formed when nitric acid reacts with barium hydroxide? So we have an acid and a base. When we combine an acid and a base, we get neutralization. And our products are a salt and water. So the HNO3 will lose the H. The BaOH will lose the OH. And those two will combine to form water. The H from the acid, the OH from the base. What we're left with is the other products, the NO3 and the BA. So looking at our answer choices here, we have H2O, HNO2, BaNO2, or BaNH2. So our products of this reaction are going to be the salt, which is BaNO3, and water. We don't have BaNO3 as an answer choice, but what we do have is water. So that is a product that is formed from the acid and base neutralization. Here's our next one. When HNO3 reacts with NaOH, what product is formed? Again, we have an acid-base reaction. Acids and base, when they react, neutralize, and they make a salt and H2O. So that HNO3 will lose that H, that NaOH will lose that OH, and the H from the acid and the OH from the base are going to make H2O. And what we're left with is Na and NO3, and those combine to make NaNO3. That means if you said D for your answer choice, you are correct. Here's our next one. Which is a product of a neutralization reaction? Acid, base, proton, or salt? When acids and base combined, they neutralize, and the products are salt and H2O. So if you said D, you are correct. Here's our next one. Which is classified as a type of acid-base reaction that produces a salt? Combination, decomposition, hydrolysis, or neutralization? Which one means when an acid-base react and the product is a salt and H2O? And if you said D, you are correct. Neutralization. Here's our next question. All right, which ions from a base will react with hydrogen in a neutralization? So we know that in neutralization, the acid gives an H and the base gives an OH, and that's what makes the water, H2O, in neutralization. So the question is asking us, what is it that reacts with the H in a neutralization? Which one? If you said OH, you are correct. Yes, the OH from the base reacts with the H in a neutralization to make water. Here's our next question. Which product completes the following acid-base reaction? So we have an acid and a base reaction. That means it's going to neutralize. And our products are going to be a salt plus H2O. So H2SO4 and KOH. The acid, which is H2SO4, is going to lose its H. The KOH is going to lose its OH. Then you're going to have H2O, which is water. And the other products remaining are going to be SO4 and K. Now, taking a look here at our answer choices below, we have H3O plus, HSO3 minus, K2SO4, or KHSO4. So, which one of these would be a product that includes the two potassiums, the two Ks, and the SO4 in the neutralization reaction? If you said C, you are correct. Good job. That was probably the hardest part of this whole session, was the equations part. That's the part that most people get tricked up on, so don't feel bad if you did get tricked up on a few of those. Hopefully my answers were able to clarify it for you. We're going to move right in to our last section and try to get this done as efficiently as possible for you. Our last section we're going to talk about is classification of acids. And there's three main types of classification that acids and bases fall into. So the classifications are Arrhenius, Bronsted-Lowry, and Lewis. Let's talk a little bit about those three different types. So Arrhenius was the first type of classification of acids and bases. It's the most simple as well. In 1884, Svante Arrhenius proposed that acids are hydrogen-containing compounds and they release that H in water. And bases contain OH and release that OH in water. So we already talked about this a little bit. So hydrochloric acid, HCl, when it's put into water, it releases its H. And potassium hydroxide, KOH, when it's put into water, it releases its OH. Pretty simple, straightforward. Arrhenius has to do with acids in water. Now, Bronsted-Lowry, he got it a little bit more complicated. So in 1923, Johannes Bronsted and Thomas Lowry proposed their theory about how acids and bases react with each other. So this is not acids or bases in water. This is neutralization, acids and bases with each other. The products of a neutralization are the conjugate base and the conjugate acid. What does that mean? So an acid plus a base are going to make a conjugate base and a conjugate acid. The acid turns into the conjugate base, and the base turns into the conjugate acid. Okay? And what that also means is that the conjugate acid is the base with an extra hydrogen. It gets that hydrogen from the acid. And the conjugate base is what the acid was minus the hydrogen, because the acid lost its hydrogen. Let's look at a few examples, and hopefully that'll clarify that as well. So we have a base, and in this case, it's H2O. Remember, sometimes water can act as a base. In this case, it did. So we have a base, H2O, and an acid, HCl, hydrochloric acid. What happens is that acid drops its H and gives it over to the base. It neutralizes. And what you're left with is the base plus a hydrogen, meaning H3O in this case, and the acid minus a hydrogen, which is the conjugate base, which is just chloride in this example. Here's another one. We have ammonia and hydrochloric acid. What happens is the acid loses its H and gives it over to the base, and the base accepts that H and now has an extra H. So the conjugate acid is the base with an extra H, and the conjugate base is an acid minus the H. All right, the last classification form is Lewis. 1923 was a busy year for classifying acids and bases because G.N. Lewis also proposed another classification of acids and bases. Basically, what he said is that a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. So acids accept, bases donate. All right, we're going to get right into our last practice questions of this session. Again, please feel free to lock your answers in as we go through them. Here is your first question. What is the conjugate base in the following reaction? The conjugate base comes from the acid. It's when the acid loses the H. So take a look at our equation here, HNO2 plus H2O. HNO2 is our acid, H2O is our base, okay? And the conjugate base is going to be when the acid loses the hydrogen. So in this one, HNO2 is our acid. When it loses the hydrogen, we're going to be left with just NO2. Good job if you said B. I know this can be a little bit tricky, but you're doing great. Make sure to read them carefully. An acid that dissociates into hydrogen ions is defined as a weak acid, Arrhenius acid, conjugate acid, or Bronsted-Lowry. Now remember, Bronsted-Lowry and conjugate are within the same realm. That's when an acid and a base react with each other. Arrhenius was the one who said that acids in water are going to dissociate or ionize and release hydrogen ions. So Arrhenius B is the correct answer. Let's go to our next practice question. What is the conjugate base of sulfuric acid? Remember, when an acid loses a hydrogen, it is the conjugate base. So sulfuric acid minus a hydrogen, we're going to end up with HSO4. Here's our next question. What is the conjugate acid of S2 minus? Okay, conjugate acid is going to result from the base accepting a hydrogen, which is H plus. So if S2 minus accepted H plus, what would the result be? If you said A, you got it correct. It would be HS, and instead of that 2 minus charge, you would add a positive charge, so it would just be a 1 minus or just a minus charge. Here's our next one. All right, what happens to a Bronsted-Lowry base in an aqueous solution? Does it donate hydrogen, accept electrons, dissociate into hydronium, or increase hydroxide ion concentration? What happens when a base is added to water? Does it donate hydrogen? No. However, it does release OH, hydroxide ions, and increase the OH concentration in the solution. Here's our next question. What conjugate base is produced when the Bronsted-Lowry acid, hydrogen phosphate, reacts with a hydroxide ion? Okay, so what this means is that HPO24 is the acid, and it is going to react with a base. Remember, the acid is going to drop its H plus, and that's going to combine with the hydroxide, OH, from the base. So it's asking us, what is it going to change into? What is HPO2 minus 4 going to change into when it drops the H plus? And it is going to change into PO3 minus 4. That's because it lost a positive charged H proton. All right, here's our next question. Sodium hydroxide, NaOH, is a Lewis base because it creates hydroxide, donates a pair of electrons, accepts hydrogen, or completely dissociates. Remember, the classification of Lewis has to do with pairs of electrons. So NaOH is a Lewis base because it donates a pair of electrons. Here's our next question. What is the conjugate acid in the following equation? So you have CH3COOH, and that is combined with water, which is serving as a base at this point. The acid loses its H and gives it to the base. Okay, the acid is then going to turn into the conjugate base, and the base is going to accept that hydrogen and turn into the conjugate acid. So H2O is going to accept an additional H plus proton and turn into H3O, which is the new conjugate acid. Here is our next question. A Lewis acid is a substance that accepts hydrogen, ionizes completely, partially dissociates, or accepts a pair of electrons. Lewis Classification has to do with donating and accepting pairs of electrons. And I can always remember Lewis acid because it starts with an A, and acids accept. So the correct answer for this question is D, that it accepts a pair of electrons. All right, you all did it. Good job. I appreciate you sticking with me through this session. We covered acid and base characteristics, pH scale, acid and base equations, and classifications. Thank you guys. Have a great day.